Our final project for ME872 is modeling of the potential field induced by opposing charges in a vacuum.
The goal of our project is to demonstrate that FEniCS can be used to model the same types of electrostatics problems that I've been using for my research, only with COMSOL. The domain for this proof of concept model represents a 3D vacuum with two spherical charge sources acting as electrodes and the bottom of the cube as ground. We compare our results directly to a comparable model in COMSOL to ensure the code is working properly.
The strong form of the partial differential equation we are solving is derived from Gauss's law, which states that the gradient of the electric flux density D is equal to the charge density. The electric field can also be represented as the negative gradient of the scalar electric potential phi, which is the variable that we are solving for. Substituting equation 2 into equation 3, and then substituting this result into equation 1 yields the strong form, which is also known as Poisson's equation. The charge density in this case is 0 because there is one positive charge and one negative charge, resulting in a 0 total charge. This causes it to take the form of the Laplace equation. The Neumann boundary conditions that were implemented were 0 charge at the outer boundaries of the box and opposing surface charges on the inner spheres. The Dirichlet boundary condition was setting the scalar potential to 0 on the bottom plate.
To implement in FEniCS, we first built the domain and mesh in Python. The cubic domain is 6 meters on a side, and the two source charges come from the two spheres located 2 meters apart at the center of the cube, each with a radius of 0.4 meters. We chose the size of the spheres and the resolution of the mesh to complement one another and to make them large enough to easily see for demonstration purposes. The weak form shown here is derived from multiplying a test function by the strong form and integrating over the domain. The Neumann boundary conditions are implemented on the right side. As you can see, the actual value of the source charge, denoted as rho plus and rho minus, has been substituted in on the spherical boundaries, and a 0 charge, denoted as rho ground, for the 5 faces of the box. The remaining boundary condition for the bottom surface of the box is a Dirichlet condition, specified as the constant 0. From here, the problem was solved using the linear solver in FEniCS.
After exporting the results to ParaView, we were able to see the electric field lines induced by the potential difference. As you can see that some of the field lines are going to ground as expected and verified by the comparison to COMSOL. Plotting the isoparametric surfaces of the potential field, you can see the positive and negative potentials surrounding each respective charge source, again verified by comparison to the COMSOL solution.
We found the implementation in FEniCS to be relatively simple once adjusted to the syntax of the Python code. We had excellent agreement with a nearly identical model built in COMSOL. This proof of concept model serves as a springboard to which I can now add much more complex and realistic combinations of materials and geometries.